This is the second of a series of 3 talks on climate change and global warming. And I put these talks together prompted by a personal need to understand the terms being bandied about and to get beyond the rhetoric of obviously biased parties. And I also felt the need to look at the evidence, come to my own conclusions as to the realities of global warming and how man-induced it was, and if and how I should react in my everyday lifestyle. Additionally, I thought it might be useful to create an information source which might help people make their own decisions. The talk is a compendium of the work of others. The information and most of the illustrations I took from the internet, and I provide credits on each of the slides. The quote at the bottom of this slide is a Yogi Berra quote, and it basically refers to the fact that there's a lot of dubious information being bandied about in regards to global warming by both advocates and deniers. And we need to be aware of where our information is coming from. In other words, beware fake news. This is a slide that we ended up with in the last talk, and in which we looked at the geological record of climate change over the last 550 million years. And during that talk, we saw that climate change is a naturally occurring, constant phenomenon. We also saw that we're currently living in an ice age or cold phase. This slide shows the temperature variation over the past 800,000 years as recorded in ice cores. The bottom horizontal axis here is thousands of years before present, with present being at the bottom right at 0, going back to, this is 500,000 years. And then the vertical axis is a variation in global temperature. Basically, as the line goes down, it's getting colder, and it goes up, it's getting warmer. The horizontal red line here is, it's basically a modern normal. Basically saying that the average temperature today, we'll zero that and see how the temperature history relates to it. What we see is a seesawing of global temperature in a regular, repetitive fashion with cold periods characterized by ice advance in the geological record, punctuated by interglacial warm periods. We see that we're currently in a warm period, in other words, an interglacial period. We also see that the temperature in the past has been warmer than today. Temperature records since 1880 from a variety of sources show that the average temperature of the atmosphere is warming. In this slide, we see time along the horizontal from 1880 to 2020, and vertically, again, a temperature anomaly showing how much the atmospheric temperature has changed. Since the mid-1970s, we see that the average global temperature has increased significantly, and since the mid-1970s by almost a degree. We're going to look at why this is. Just as a point to note, the current rate of warming is approximately 10 times faster than that experienced at the end of the last cold phase that we saw in the last slide. The predicted rate of warming for the next century is at least 20 times faster than those demonstrably natural phenomena. The ice core data that we looked at last time showed us that, like for temperature, the atmospheric concentration of carbon dioxide has also been fluctuating. In the red here is the temperature data that we looked at in the last graph. We also, in this graph, show carbon dioxide concentrations. And you can see that the two curves are very similar and at first glance appear to parallel one another. However, close examination of the correlation between these two, temperature and CO2, indicates that there are lags between them. This indicates that although carbon dioxide is likely an important factor in natural climate change, it doesn't appear to be the be-all and end-all controlling factor. Correlation does not necessarily equate to causation. We need to be careful about that. There are a number of elegant theories about the triggers for the sudden initiation of the warm periods that we see here, 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 and here, I'm not going to go into those now. All of them involve a complex interplay of multiple factors, and there's no definitive answer yet found. That's a subject for a complete talk in itself. Here we're looking at the carbon dioxide curve for the past 800,000 years. As we saw, it goes up and down, ranging between about 180 parts per million and 290 parts per million, except in the very recent past and present, where we see a meteoric rise in atmospheric concentration of carbon dioxide. I'm sure you've heard about this, but you may not be familiar with just how significant a rise in concentration there has been. Since 1950, the CO2 concentration has risen from 300 parts per million to 415 parts per million, almost a 40% increase. And I have to say, when I first saw this, the hairs on the back of my neck rose. I was shocked. And it was this graph which actually prompted me to do this work and to put these talks together. The current CO2 concentration of 415 parts per million appears to be higher than it has been for the past 14 million years. The recent rapid rise in carbon dioxide concentration is demonstrably due to industrial activity, agriculture, and deforestation. The big question, though, is how much is the recent human-caused rise in CO2 in the atmosphere responsible for the significant temperature increase that we saw? And this is where there is plenty of heated debate. This is just to show, this is the point we're looking at, and we'll be looking at for the rest of the talk here, this meteoric rise in carbon dioxide concentration. This is just some of the detailed information year by year showing it as a constant rise. What this slide shows is a strong correlation between the recent atmospheric temperature increase, shown in black, and the carbon dioxide concentration increase, shown in red. It's unmistakable. Okay, well, let's look at the atmosphere. As we saw in the previous talk, the atmosphere today is composed primarily of nitrogen, 78%, and oxygen, 21%. These two gases, along with argon, which is just under 1%, make up 99.9% of the dry gas volume. Of the remaining trace gases, carbon dioxide is the most voluminous, over here on the right. It makes up about 94% of the trace gases. We also see methane, nitrous oxide, ozone, etc. But carbon dioxide is the biggie there, followed by methane and then nitrous oxide. Although carbon dioxide makes up only about 0.03% of the gases in the atmosphere, it belongs to an important family of gases that have a profound effect on retention of radiative energy from the sun in the form of heat due to the physics of their molecular structure. This family of gases is called the greenhouse gases. So what are these greenhouse gases that we keep hearing about, and how do they work? This is a short video I'm going to show you, which explains in simple terms what they are and how they work and why they're important to us.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius. And even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiated heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
So, jiggle and shake. Let's just think about that's how greenhouse gases work. This slide here shows on top left a map of the world showing atmospheric sampling locations used to monitor changing atmospheric composition. There are three principal greenhouse gases: carbon dioxide, methane, and nitrous oxide. The graph lower left shows that the concentration of these gases has increased significantly since the beginning of the Industrial Revolution, which was about 1750 and marked here on the slide. To the right, everything post-industrial, post-1750, and we can see that the nitrous oxide, methane, and carbon dioxide concentrations start rising then, and basically it's an exponential increase. The columns on the right, with the blue columns on the right here, show the percentage increase in concentration of those three gases since the start of the Industrial Revolution. Methane, 259%, carbon dioxide, about 150%, and nitrous oxide, about 123%. These are pretty significant increases. The blue line on this graph, time is on the bottom, and various concentrations, I'll talk about it in a second here. This blue line here just echoes again the increase in carbon dioxide concentration since 1750 that we saw previously, from 280 parts per million to 415 parts per million today. The black line here shows the increase in concentration of all greenhouse gases in the atmosphere, normalized as being as if they were all carbon dioxide. Note the following. We see a steady increase through time in the relative contribution of non-CO2, the black line, versus just carbon dioxide. In other words, the gap between the blue and the black gets larger with time, which indicates that the other greenhouse gases and CO2 are increasing in concentration. We're introduced to the right to what's called the annual greenhouse gas index. And this is basically the capacity of the Earth's atmosphere to trap heat due to the properties of greenhouse gases. At the start of the Industrial Revolution, the AGGI is normalized at 0, saying that's the normal atmosphere. And as we increase the greenhouse gas concentrations in the atmosphere, we increase the heat trapping capacity of the atmosphere. And what we see is that the AGGI has increased markedly since 1950. Just shoots right up. So what are some of the other greenhouse gases besides carbon dioxide, and why are they so important? This graph illustrates the greenhouse efficiency of various important greenhouse gases relative to carbon dioxide. Carbon dioxide down at the bottom with a concentration in the atmosphere of 415 parts per million. If we compare volume to volume, it's of course 1. The warming potential of carbon dioxide compared to itself is 1. Methane, we saw, is another important greenhouse gas. It has 28 times the heating capacity than carbon dioxide. Its concentration is 1.8 parts per million. These hydrofluorocarbons, don't you just love these names? This is a family of gases, and they're 138 times as potent than CO2 volume per volume. And just going on up, nitrous oxide, 265 times more powerful than CO2. And these perfluorocarbons, they're, well, over 6,600 times as powerful as CO2. And right at the top in here, sulfur hexafluoride has a warming capacity of 23,500 times that of carbon dioxide. So you can imagine any increase in gases like these top ones here will have a significant effect on the heating capacity of the atmosphere. And this was recognized a while ago. And this is when the danger of these pollutants was recognized, countries came together in Montreal to sign what's called the Montreal Protocol. And it came into force in 1989 with the idea of limiting emissions of these compounds. And you may remember that a lot of the refrigerants were switched out because they were using chemicals which were destroying the ozone and also increasing the heating capacity of the atmosphere. However, there is some evidence that signatories of the Montreal Protocol are not really keeping their word. And that's illustrated by this 2019 headline that I got off the CBC News. Greenhouse gas with 12,000 times the heating capacity of CO2 shows a surprise rise in the atmosphere. Trifluoromethane, this is the one family which has 123 times or whatever of the capacity, heating capacity of carbon dioxide, a byproduct in the production of refrigerants. Major producers, China and India, report drastic emissions cuts. However, atmospheric gas measurements suggest otherwise. Measurements at 5 stations around the world show that emissions of HFC 23 reached a record high in 2018 of almost 16,000 tons. And that was a lot higher than the 2,400 tons of emissions of that gas reported by China and India to the UN Environment Program in 2017. Obviously, there's a bust somewhere. Based on China and India's reports on their emission levels, scientists had expected to see HFC 23 levels drop by 90% between 2015 and 2017. But that wasn't happening. So something's not right. Either someone's not measuring something correctly, or someone is not telling the truth. There are also other problems that have been run into with regards to these very powerful greenhouse gases. Some of the chemicals being used as replacements for the ozone-eating chlorofluorocarbons, they break down into the atmosphere into new nasty contaminants. And so unfortunately, the solution that we thought was there ain't, and we have to look for new solutions. There was a comment in May by a scientist. The Montreal Protocol was probably one of the best regulations out there to involve all the countries at once. But then, of course, you have these unintended consequences. We don't have all the answers, in other words, and we have to keep being very careful. This colorful graph shows 2 things, basically. There's time along the bottom, 1979 to 2019. What it shows is the change in heat retention capacity of the atmosphere from 1979 to 2019, and the contribution of the individual greenhouse gases to this change. The left axis shows what's called radiative forcing. And radiative forcing basically is the difference between the amount of energy retained in the atmosphere versus the amount of energy reflected back into space that arrives at the Earth from the sun. So the higher the radiative forcing value is, the more heat retention capacity there is in the atmosphere. The vertical axis on the right measures this annual greenhouse gas index that we talked about. This being, as I said, a measure of capacity of the atmosphere to trap heat. The AGGI is indexed to 1 for the year 1990. The green line just added into the graph shows that both radiative forcing and AGGI have increased significantly between 1979 to 2019. The total greenhouse gas index has changed from 0.8 in 1979 to 1.43 in 2019. That's a 78% increase in warming capacity. Beneath the green line, we see a number of color bands. Each color band illustrates the contribution to this warming effect by a particular greenhouse gas. The key to the colors is top left. CO2 is this light blue color here. Methane is this greenish color. Nitrous oxide, this purple, and on down. We can see from this graph that by far the biggest warming effect is associated with carbon dioxide. We saw that carbon dioxide is not the most powerful greenhouse gas by unit volume, but it is by far the most common greenhouse gas, hence its dominating effect. Most of the total annual greenhouse gas index of 1.45 that we have today is produced by carbon dioxide. Methane and nitrous oxide are also very significant. So are these CFCs. Okay, so we know that emissions into the atmosphere of greenhouse gases are ongoing and are significantly affecting heat retention by the atmosphere. So who's doing the emitting? Well, the answer is we all are, but to varying degrees. In 2017, a global total of 36 billion tons of carbon dioxide equivalent greenhouse gases were emitted into the atmosphere by human activity. I stress that's 1 year's emission into the atmosphere, 36 billion tons. The pie chart in the lower left here shows the greenhouse gases that were emitted by the US into the atmosphere in 2018. We see that 81% of the total US emissions for 2018 of 6.7 billion metric tons of carbon dioxide equivalent was in the form of carbon dioxide, followed by 10% as methane, 7% as nitrous oxide, and 3% as fluorinated gases. This pie chart is for the US only, but one for the world, I could only get one for 2014, showed a very similar pattern for the entire world. So we can see that the bulk of greenhouse gas emissions are carbon gases, carbon dioxide and methane, and together they make up over 90% of the total greenhouse gas emissions. The chart on the right for the year 2017 shows that China at 27.2% and the United States at 14.6% are by far the biggest current individual emitters of carbon into the atmosphere. Together, they make up almost half the total global output. Other important players are India, Russia, and Japan. Canada emits 1.6% of the global total. Well, let's look at this by continent. We see that Asia is the primary source of greenhouse gas emissions today, about 53%. North America produces about 18%, Europe 17%. So these three continents are the biggies. Africa produces about 4%, South America 3%, and Oceania, including Australia, about 1.3%. Look at international aviation and shipping. These activities are pretty significant. They produce collectively 3.2% of total CO2 emissions in the world. So when we look at this, we look at Asia and we say, my golly, those guys are really pumping it out. Well, they are, but Asia accounts for 60% of the world's population, 53%. North America, with 8% of the world's population, is 18%. And Europe, with 10%, 17%. So there are lots of ways to skin a cat, and there are lots of ways to point the finger. But when related to population, Europe and North America are by far the heaviest emitters per capita. This slide shows total carbon dioxide emissions and who has done what since the start of the Industrial Revolution in 1750. We can see between 1750 and 1850, the emissions were negligible. But what we see is that the beginnings of the Industrial Revolution were in Europe. So the yellow relating to the EU countries in Europe are the longest lasting. And then pretty soon afterwards, in late 1800s, early 1900s, the United States industrial machine started kicking in. What we see is that European emissions have been decreasing recently, while those of the US have been relatively steady for the past 30 years. The big story is China in this red here, which shows rapid and significant increase in emissions over the past 30 years, with very significant recent increases here. So who's produced the most carbon dioxide emissions over time? This chart shows that North America and Asia have each cumulatively produced 29%. Europe, 33%. Remember, Europe has by far the longest history. And the rest are small potatoes. Country-wise, the US, China, and the EU figure as the major cumulative producers. This figure charts the percentage of carbon dioxide produced by whom over time. Remember, early in the Industrial Revolution, 1750, Europe was the only one with any industrial activity. Then the US kicked in here. And what we see is that the percentage contribution by Europe diminishes through time, percentage contribution by the United States diminishes, but China and Asia Pacific now are beginning to really take over by expanding their contribution. This slide looks at the effects of wars, pandemics, and political events on carbon dioxide emissions. Basically, we see that at best, they're minor blips in an inexorable rise in global carbon dioxide emissions into the atmosphere. Right at the end here, and I'll show this again in a little while, we see that there's a forecasted downward blip associated with COVID, about a 5% decrease over 2019 emissions is anticipated due to the various shutdowns that have occurred with COVID. The question is, will we change our behavior, or will we just get a little minor blip here, and will it continue to keep on rising? To change it, we're going to have to change what we do. I'm going to show another movie in here. One of the problems convincing people about climate change is that you can't see it, and that climate changes tend to be subtle and over a period of time. We have for a number of years been able to chart emissions on a global scale, but what I'm going to show you now is a model which is based on data for the year 2006. And what it shows is throughout the year 2006, the varying emissions of carbon dioxide and carbon monoxide. So sit back, watch and listen to the dialogue as the major seasonal changes in emissions are explained.
Hi, this is Bill Putman. I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural large-scale weather patterns within the global circulation. During spring and summer in the Northern Hemisphere, plants absorb a substantial amount of carbon dioxide through photosynthesis, thus removing some of the gas from the atmosphere. We see this change in the model as the red and purple colors start to fade. Meanwhile, in the Southern Hemisphere, we see the release of another pollutant, carbon monoxide. This is a gas that's both harmful to the environment and to humans. During the summer months, plumes of carbon monoxide stream from fires in Africa, South America, and Australia, contributing to high concentrations in the atmosphere. Notice how these emissions are also transported by winds to other parts of the world. As summer transitions to fall and plant photosynthesis decreases, carbon dioxide begins to accumulate in the atmosphere. Although this change is expected, we're seeing higher concentrations of carbon dioxide accumulate in the atmosphere each year. This is contributing to the long-term trend of rising global temperatures. The Orbiting Carbon Observatory 2, or OCO2, will be the first NASA satellite mission to provide a global view of carbon dioxide. OCO2 observations and atmospheric models like GEOS-5 will work closely together to better understand both human emissions and natural fluxes of carbon dioxide. This will help guide climate models toward more reliable predictions of future conditions across the globe.
All right, so that was carbon dioxide and carbon monoxide. Now, what we're quite a recent innovation is satellite coverage, which basically is able to show us real-time concentration variations and concentration distributions of various greenhouse gases in the atmosphere. Your screen is showing two maps of the world. On top here is one for May the 16th, 2020, and on the bottom one for October the 24th, 2020. And basically what we're looking at is methane concentration across the world for these two dates. The hotter the colors, the higher the concentrations. And what I'd like you to look at is the difference between the middle part of the Earth here, Africa, India, and China in particular, some of the United States, between May 16th and October 24th. You see October 24th, there's a lot more hot colors indicating a lot higher methane. These maps are produced by a company called GHGSat, and they've launched satellites specifically to identify and track methane and various other greenhouse gas emissions. And what we're looking at here is May 16th was a time during significant COVID lockdowns and reduced industrial activity. And while there is seasonal variation for sure to be considered, a lot of the difference between the May and October methane concentrations is due to the resumption of industrial activity. So the main point of this slide and the last one is that we are actually able to see greenhouse gas emissions now into the atmosphere, and that makes climate change that much more tangible. So what about the future? We've seen we're able to record and monitor the changes in atmospheric concentration, and we've seen that these are linked to human activities. We know these gases act to retain heat in the atmosphere. So a question is, what sort of effect will this have on our climate through time? This is where Yogi Berra's quote becomes relevant. It's tough to make predictions, especially about the future. And we've seen that controls of climate change are varied, and the interaction of these controlling factors are complex. So any prediction of what the future holds for global warming and climate change will be complex. A man called Svante August Arrhenius, working in the late 1800s and early 1900s, is generally recognized as the father of climate modeling, trying to predict the effect that man's activities are having and will have on the Earth's climate. Arrhenius deduced in the 1890s that man's industrial activities, and in particular burning fossil fuels such as coal, were changing the composition of the atmosphere, and that this could affect climate. Interestingly enough, Arrhenius is related to Greta Thunberg. Today, supercomputers are used to run extremely complex four-dimensional models of the Earth's climate. The fourth dimension is time. These models are made up of millions of cells of data, which attempt to depict the Earth's oceans, land masses, and atmosphere, and circulation systems, and what happens to them when factors such as greenhouse gas concentrations with their associated cumulative AGGIs are changed through time. This is just a depiction of the multiplicity of information that goes into these sophisticated computer models. You can imagine how complex these become, and this complexity opens the door to controversy. Another Yogi Berra quote, God, you gotta love the man. All these models need careful, unbiased scrutiny and clear statements as to their limitations. And given the complexity of the natural system, we must be extremely careful in believing our complex but still simplistic models. So Yogi Berra's quote, in theory, there's no difference between theory and practice. In practice, there is a suitable comment on climate modeling today. We need to be careful about it. However, there are strong indications that climate modeling, which shows increased temperature in the atmosphere associated with continued greenhouse gas emissions, is on the right track. There's plenty of evidence for that. This slide, based on observation, which is the black line showing temperature going up, and computer modeling, the pink and blue bars, shows different scenarios of average temperature through time based on different model input assumptions. Over the time period shown, 1900 to 2000, if greenhouse gas concentrations are maintained naturally, we see that atmospheric temperature deviates only slightly, and this is indicated by the blue band. If we incorporate continued emissions of greenhouse gases by man's activities, along with natural phenomena such as volcanic eruptions, there's a sharp rise in atmospheric temperature. This is shown by the pink. And we can see the pink band here parallels the black, which is the actual observed behavior in the climate. So this modeling suggests that industrial greenhouse gas emissions are having a significant warming effect on the atmosphere. So how warm are we going to get? Well, it depends on what we continue to put into the atmosphere. The black line on the left shows a temperature increase experienced since 1990 as compared to the average temperature for the years between 1971 and 1999. I don't know why they picked those years, but they did. What we see with these two yellow lines is that we see in 2020, we've almost experienced 1 degree of warming since 1990. 3 scenarios of projected temperature increase from now until 2100 are based on varying models of greenhouse gas input. We get a low model of low greenhouse gas input in blue, a medium model, medium greenhouse emissions, and a high model with high greenhouse gas emissions. What this graph shows that by 2100, we can expect to have experienced between 2 to 4 degrees of warming in the atmosphere. So what will this do? Well, we're not quite sure at the moment. The third talk that I'm going to give will look at what's happening in the world associated with global warming, the effect it's having on our environment, landforms, sea levels, etc. But there are a number of potential tipping points which we are quite concerned about. And these are, first of all, a potential collapse of major ice sheets in Greenland and Antarctica. The melting of both of these would result in dramatic changes in sea level and potential disruption of the oceanic circulation patterns that we know today. And we know that Western Europe, for instance, is dependent on the Gulf Stream for its temperate climate. If the Gulf Stream stopped bringing warm water up from the Gulf of Mexico to offshore British Isles and France, that area would experience significantly colder climates. Another thing we're worried about is if we get significant warming and the oceans warm up, we'll see sudden release of vast amounts of methane, which are currently stored in Arctic permafrost and in seafloor hydrates. You may remember in the model we saw with the carbon dioxide and carbon monoxide for 2006, the commentary mentioned that about half of the annual emissions are absorbed by the ocean and by photosynthesis. The other half goes directly into the atmosphere and stays in the atmosphere. Well, there is a potential limit to how much the oceans can actually absorb. And there is the potential that the oceans become carbon dioxide saturated and unable to absorb any more. And the result of that is that more of the CO2 remains in the atmosphere and thus accentuates the greenhouse effect. And also, the more CO2 that gets absorbed into the oceans acidifies the oceans and has an effect on marine life. These are potentially significant tipping points, which we don't fully understand. So we've been talking about average change in average global temperature. What we need to understand is that the average temperature that we've been quoting is a statistical construct and doesn't have any meaning in reality. The simple fact that it's cold in Canada at the same time that it's warm in Mexico should tell you that temperature is not averaged across the world in reality. What these maps show modeled across the globe they relate to two different temperature scenarios. The one on the left, these two maps on the left relate to a 1.5 degree change in average temperature between now and 2100. The one on the right is a 2 degree temperature change between now and 2100. The top maps show the change in average temperature of hottest days. And what we can see in both these is that there's sort of a general across the world change in temperature of the hottest days experienced during a year. However, when we look at the change in average temperature of coldest nights, the effect is startling. What we see is there's a huge temperature effect in the high latitudes, both north and south. And whereas change in average temperature of hottest days is in around the 1 to 3 degree range, the change in average temperature of coldest nights in high latitudes is up to 8 to 10 degrees. It's a startling amount. And what this indicates is that the vast most of the effects of global warming are going to be felt in the high latitudes in places like the Canadian Arctic. What we'll see is that our weather patterns will shift, already are shifting if you talk to many. Our winters, which currently are cold, will become less cold, less extremes experienced, whereas the summers, which are warm and hot, will become hotter, and an overall shift in average temperatures to warmer. And this has a connection to the weather. This slide explores the relationship between global warming and extreme weather events. The strength of relationship between the two is shown increasing from weak on the left to strong and strongest on the right. There's relatively weak evidence that global warming is causing droughts, tornadoes, and forest fires, although if you live in Australia or in California, people would dispute this. But there is definitely stronger evidence that global warming causes increased incidence of hurricanes with associated storm surges and also heat waves. There was an article today just published that was saying that the hurricanes are more intense, and the greater intensity of hurricanes due to global warming will mean that these hurricanes go further inland and cause further effects, cause significant damage further inland than was previously the case. This graph basically shows what you saw on the last slide, but in graph form. Extreme weather in the form of floods, storms, and droughts is on the rise through time. Okay, so what are we doing about global warming? Well, there are a number of international agreements. The Kyoto, Copenhagen, and Paris agreements were attempts to get countries to agree to limit greenhouse gas emissions through changes in technology, reduction in energy, etc. Let's look at the Paris Agreement. The aim of the Paris Agreement, which was held in 2015, was to create a comprehensive, legally binding climate treaty that would require all countries, including major carbon emitters not abiding to the Kyoto Protocol. China and the US did not participate, and we saw that they too are the two major greenhouse gas emitters in the world. The Paris Agreement was trying to get them to limit and reduce their emissions of carbon dioxide and other greenhouse gases. However, the wording of this agreement was watered down at the 11th hour by the US during the Obama administration, which insisted on changing at the last minute the original wording shall to should throughout the document. And the importance of this is highlighted by Article 4 below. And just in your mind, replace should by shall, and you'll see the difference. Developed country parties should continue taking the lead by undertaking economy-wide absolute emission reduction targets. Developing country parties should continue enhancing their mitigation efforts and are encouraged to move over time towards economy-wide emission reduction or limitation targets in the light of different national circumstances. There's no doubt that if the should, which was finally signed, was replaced by shall, that would have been a much stronger statement. This is the Paris Agreement, the guts of it, basically. It includes clauses on control of global warming, emissions, developed countries helping developing countries, etc. Temperatures. The idea was to keep global warming well below 2 degrees Celsius by 2100. Finance. Rich countries must provide $100 billion from 2020 on as a floor, that to help developing countries keep their carbon emissions low. Developed countries must continue to take the lead in the reduction of greenhouse gases. Emissions objectives aim for greenhouse gas emissions to peak as soon as possible, and from 2050 achieve rapid reductions. Burden sharing. For all this, we're going to change our ways. Developed countries must provide financial resources to help developing countries in reduction of greenhouse gas emissions. It was a review mechanism every 5 years. And a recognizance that certain countries were much more vulnerable to the effects of climate change than others and needed special assistance. This is all fine and dandy, very altruistic and somewhat utopian. However, there was no mechanism in place to enforce compliance with the Accord's provisions. There was to be a committee set up to promote compliance, and this committee was to function so as to be transparent, non-adversarial, and non-punitive. How effective do you think that would be? The goal of the Paris Agreement is to limit greenhouse gas emissions sufficiently to limit global warming to 1.5 degrees by 2100. So there's the goal, 1.5 degrees. You can see that according to this, by this report, which is a September 2020 report, we've already experienced 1.1 degrees of global warming. We got 0.4 degrees to go in 80 years left. Pledges and targets from the participants and signatories of the Paris Agreement put us on track for warming of 2.7 degrees warming by 2100, well above the 1.5 degree goal. And current policies and emissions of the signatories have us on track for actually 2.9 degrees of warming. So you can see from this that the 1.5 degree goal by 2100 set by the Paris Agreement is pretty aggressive, if not unattainable, unless there's some immediate change in behavior. This slide shows the inexorable rise in CO2 emissions that we saw through time to the current level of about 36 billion tons a year. It shows the forecasted 5% reduction in greenhouse gas emissions associated with COVID-19 shutdowns. Beyond this, it shows what has to happen to greenhouse gas emissions if we're going to meet the 1.5 degree target by 2100. What you're seeing is a precipitous drop in greenhouse gas emissions. Critical to attaining the 1.5 degrees is achieving carbon neutrality by 2050. And by carbon neutrality, this basically means that if you put a unit of carbon dioxide into the atmosphere, you have to take away a unit of carbon dioxide, so there's a negative balance, so there's a neutral balance. Some climate researchers are optimistic that the COVID-19 pandemic has taught governments some critical lessons that they can apply to the problem of rising temperature and gas emissions. However, currently the focus seems to be on economic recovery rather than greenhouse gas emission reduction. Many energy experts believe there'll be a bounce back in emissions next year, but hopefully that long term the world will move to greener fuels. As we said, the question is, will the reduction in greenhouse gas emissions be enough, soon enough, or deep enough to keep temperatures down to what people think are safe levels? The big challenge is to ensure the post-pandemic economic recovery has a green focus. This is a 2019 map showing which countries ratified the 2015 Paris Agreement. So you can see quite a lot of countries did, 185. A total of 195 were signatories. Notable in this map, as I said, 2019 map, was the US plan to exit. And that was pretty disturbing because the US, with about 15% of the total global emissions, is the second highest greenhouse gas emitter at the present time. Biden has stated that on day one of his administration, the US will rejoin the Paris Agreement. Let's hope he does. Okay, so how's everyone doing in relation to their Paris Accord commitments? Not so good, according to this September 2020 map. Of the major players emitters, we can see that China is highly insufficient. The US, critically insufficient. India is doing better. It's compatible for 2 degrees, but doesn't meet the 1.5 degree goal. Russia, highly insufficient. Canada is insufficient. Obviously, this puts the 1.5 degree goal in serious jeopardy. Countries made nice words at the time, but appear not to be doing too much to live up to their commitments. A little bit more about this in a moment. So what activities produce the most greenhouse gases? This slide shows the source of greenhouse gas emissions by activity sector. The energy sector is by far the biggest greenhouse gas producer, shown in this dark blue, followed by transport, shown in orange. Emissions from both continue to grow, as does the total amount of emissions. This is a breakdown of the energy sector, showing what makes it up. By far the most energy is provided by the use of fossil fuels, coal, oil, and gas. The use of these is directly responsible for the majority of greenhouse gas emissions associated with this sector. So there's a huge dependence on fossil fuels. And what we see is there's not much evidence globally of a decrease in emissions of either coal, gas, or oil at the moment. We've seen in earlier slides the inexorable increase in greenhouse gas emissions year upon year. Does this mean that nothing is being done to curb the emissions? Well, the answer is no. Things are being done, but not enough to produce a reduction in total emissions year by year, yet. This slide shows the breakdown of activities leading to an increase in greenhouse gas emissions from 32.6 billion tons in 2017 to just over 33 billion tons in 2018. Current emissions around in 2020 are over 36 billion tons. Economic growth by itself would have increased emissions from 27 to 2018 to over almost 34 billion tons. But there are a number of mitigating factors which have reduced this. We see increased energy efficiency, the use of renewables, switching from coal to gas, increased nuclear, and a number of other initiatives which have brought the overall potential emissions from close to 34 billion tons down to 33, just over 33. So that's the actual increase that we saw year upon year. So there are things being done to try and reduce greenhouse gas emissions, yet retain growth in our economies. Let's look at Canada. As we saw from the map a little while ago, Canada is performing insufficiently with regards to our Paris Accord commitments. This is 2018 data here on this slide, but I believe it to be reasonably current. The top left chart shows a relative flattening in our overall greenhouse gas emissions at just over about 730 megatons of carbon dioxide equivalent. But the trend is pretty flat. The top right is a sort of feel-good in that it shows an increasing efficiency trend with less greenhouse gas emissions per capita and per unit of GDP. This feel-good, though, is offset by the growth of our economy. Bottom left shows the distribution of greenhouse gas emissions by province or territory for 3 different years, 1990, 2005, and 2018. We see that major emitting provinces include Quebec, Ontario, Saskatchewan, Alberta, and BC, with Ontario and Alberta being by far the largest emitters. Saskatchewan and Alberta can be seen to be the bad guys in that their emissions continue to grow while the other ones are generally staying stable. The chart in the bottom right shows the inexorable rise in greenhouse gas emissions associated with the oil and gas and transportation sectors. The reason why Alberta and Saskatchewan are so high, of course, is due to the oil and gas sectors in both those provinces. There was an article today which said that the methane emissions from oil and gas activity in Alberta had actually been underestimated by 50%. So this chart here may look even worse than what is shown in here. So what does Canada need to do to decrease its greenhouse gas emissions and comply with its Paris Accord commitments? Here are some words from government publications. Canada will need to fundamentally transform all economic sectors, especially patterns of energy production and consumption. This requires major structural changes to the economy and the way people live, work, and consume. The electrification of end-use applications that are currently using fossil fuels is fundamental. For example, using electricity to power certain cars, trucks, building appliances, and heating systems. Carbon pricing will be an important element to achieving this objective. So the government recognizes we have to move away from fossil fuels. So what does the world need to do to reduce greenhouse gases in our attempt to limit global warming? Well, there are two basic approaches we can take. The first is to reduce greenhouse gas emissions by reducing our energy requirement, increasing energy efficiency, and changing energy sources. This is happening, but not fast enough. This picture here is a photograph of the destruction of big cooling towers associated with coal-fired power plants in Germany. Germany is moving away from coal as an energy source. Global carbon dioxide emissions from the power sector fell by 2% in 2019, owing to reduced coal usage in Europe and the United States. However, there's a lot of chatter, and you can understand the concern of people in Alberta associated with moving to a green solution and dumping or moving fast away from fossil fuels. Their livelihood depends on it. So any change in energy source has to take into account the people aspect. What I've written in here is beware collateral damage in the change to a green solution. We must facilitate the transition by retraining people, providing them jobs, refocusing their efforts and activities. We also have to minimize the impact of required industries such as mining of lithium, lead, zinc, copper, etc., which are so important in the electrification of the energy industry. Lots of potential damage to the environment through those mining activities. The other option we've got is to reduce the greenhouse gas concentrations currently in the atmosphere. And this is done through what is called geoengineering. Some of this is pretty radical and controversial stuff. The slide shows the various ways that existing concentrations can be reduced. Some of the ways are conventional, such as tree planting and forestry expansion, increasing the use of industrial scrubbers and injecting carbon dioxide into underground reservoirs. Others are radical and potentially scary. These include large-scale planting of genetically modified or geoengineered plant crops, spraying aerosols into the atmosphere, creating clouds via misting vessels, and even setting up giant stationary orbit sun shields to reflect the sun's energy out of our system. Some seem downright wacky. Wrapping glaciers in high albedo material or scattering reflective particles on the top of glaciers and ice caps to insulate them and increase the albedo of the Earth. We'll see some of this. We already are seeing some of this to try and reduce, but there will be more talk about geoengineering. In fact, there was an interview on the CBC just last week about geoengineering. There are hopeful signs. There's evidence that countries are taking heed and putting their money where their mouth is when it comes to controlling greenhouse gas emissions. These countries have recently, and some very recently, enacted laws to meet net zero carbon emissions. Sweden was the first in June of 2017 to say that they were going to be net zero carbon emitters by 2045. That was followed by the UK, France, Denmark, New Zealand, Hungary, and then China in September said they would be doing it by 2060. Japan in October, just last month, and North Korea just last month by 2050. So there is hope and there is some action. Who else will have done this by the next major international climate meeting, which is scheduled for November 2021 in Edinburgh. That was supposed to be in 2020, in other words, right now, but was deferred a year due to COVID. Will the US under Biden do that? Don't know. So just wrapping up, main points to take away from this talk. Greenhouse gases affect atmospheric heating. Human activities are increasing the concentration of greenhouse gases in the atmosphere. Global warming is occurring. The degree to which human activities are contributing to global warming is a point of significant debate, and some of it is not necessarily scientific. Modeling of future global warming is complex, and partly due to its complexity is controversial. Practically no one is living up to their climate accord commitments, and there's no way to enforce compliance. Reducing greenhouse gas emissions will take global cooperation. Fossil fuels and transportation are key contributors to greenhouse gas emissions. Replacement technologies must be phased in without negative implications for people or the environment. And there are signs that maybe the world is beginning to take notice and act. So another quote from Yogi Berra: "The future ain't what it used to be. Whatever the solutions we arrive at, and we need to arrive at them, we do need to arrive at them, that's for sure. The future ain't what it used to be, certainly not what it was in 1750. That's the talk. Thank you very much, everyone.